Give me a moment.
तो ऐसे फाउंड आउट नारुतो के पीछे ही था। हाँ।
Okay, I'm recording. There are three plus three, seven. Okay, so that's not bad. Seven people in attendance. Lucky, Saumil, Ayan, Ronald, Sandeep, Ryan, and Siddhant. Have I missed anybody? If you're sharing, listening to it, we're sharing room. Okay, that's good. Let me share my screen, and I'll. Oh, there's something in the chat. Oh, that's okay. See, I never ever force people. Health is the most important thing in life, okay, and that you will have to take care of. So I'll never ever, I'll be the last one to force you to attend when there is a legitimate reason, most important being health. Okay, so you are certainly excused, Ayan. So don't strain yourself and attend, and then be attentive to the extent that you can. I'm okay if even if you take rest. Thank you. Okay, can you see my screen? Okay, now first let me summarize. Where we are at this time. Okay, what we have seen so far. mm, okay. Um, Yeah, we've introduced transition systems as a general purpose formalism for modeling and computational systems in general at at a chosen level of abstraction. Okay, I can get into more details. This is only a summary. So transition system, it allows you to represent the state of your system in a chosen level of abstraction, and it also allows you to computational systems are time sensitive system in the sense there's some evolution over time where the notion of time can be very abstract, and transition relation, which is a component of transition system, allows you to define your at whatever level of abstraction that you would like to model the evolution of time in terms of the step that it does. Now, then we saw how to model sequential and concurrent program behavior as set of traces as the system evolves as a transition system. Okay. And we saw how to encode the transition system in first order logic. We spent a little bit of time in specifying, looking at what kinds of properties are of interest, where a property here means a constraint on an expected constraint that is supposed to hold on the set of behaviors, I mean, on the behavior of your program, that is set of traces. We saw three kinds of properties: invariant properties, safety properties, and liveness properties. The temporal logic, I made the observation that temporal logic is an appropriate formalism for specifying constraints on sets of traces. We didn't introduce it formally, but I defined it informally and noted that a tool like Euclid is allows you to specify these things, allows you to define a transition system. It gives you all the wherewithal to define a transition system, even for concurrent programs with with support for both for synchronous and asynchronous concurrency, and then you can start you can specify these properties. Okay. Then we spent a couple of lectures on looking at bounded model checking, which is a symbolic technique for verifying absence of bugs of bounded length. Okay, there is a measure of what this bounded length is, and this is done by incrementally unrolling the single step transition relation T, which is part of the definition of the transition system. And the length, the bounded length here, that measure is measured in terms of the number of unrolling of the transition relation. Of course, this is, yeah, so by definition is meant to be an incomplete method, but it is very effective, turns out, in practice to get deeply embedded bugs that even random testing will not would not be able to. There was one example that I didn't show in in one of the lectures. Maybe when I locate that, I will show that. That kind of illustrates why even symbolic execution, let alone bounded model checking, can reveal deep, bugs that require a lot of deep simulation runs using shallow symbolic execution techniques. And that's the motivation and rationale for the popularity of the power and the popularity of BMC in practice. Then we spent some time in trying to define completeness threshold to make bounded model checking complete. A completeness threshold is a measure, that gives an upper bound, is a measure which is a function of the structure of your transition system, which gives an upper bound, even if not precise bounds for this K, for how long you need to run a BMC, how far you need to unroll in order to ensure that your property is true. Okay, it holds for all traces. And we also saw how to compute those completeness threshold using, using SAT solvers. And in general, those completing those completeness thresholds is very hard. It's as hard as p-space complete, as we noted, because it had, in order to express those completeness threshold as a SAT instance, you needed quantifier alternations, precise bounds, I mean. Okay. And we saw some loose bounds that can be used, which are somewhat easy to compute by expressing them as a SAT solving instance. Okay. Then we, started looking at CBMC, a tool, a bounded model checker tool, for ANSI C programs. Now, this one um, optimizes, I mean, like I said before, Euclid gives you that's, I mean, yeah, I have not introduced you to Euclid yet, which, oh, sorry. I needed to, just give me a moment. Although I started the thing, no. That's okay. Yeah, I don't need to, do I need to record it? I don't think so. Yeah, okay. This is about, yeah. So Euclid allows you to, it gives an input language which is much like not like C but a cleaner version of C to define your transition system directly. Okay. uh, and it also allows you to prove programs. And, it provides certain features for tailoring it to sequential program. But here's CBMC, so you could do transition system BMC. It supports a BMC engine, and you will see that you could do model checking, you can do BMC at the level of transition system in Euclid. Whereas CBMC is a bounded model checker tool, which is optimized to some extent and tailored to support BMC for sequential software, specifically for ANSI C programs. Um, Here we noted that unwinding at the level of transition system where the transition system model of sequential program, where the sequential program is modeled using PC, which is what we saw, okay, in class, and how it could be automatically generated, kind of doesn't make sense for when you're talking about unwinding programs and so on. What makes sense is when you do the unwinding, because primarily in sequential programs, the source of I mean, the main construct that produces traces is are loops, and therefore it makes more sense to do the unwinding at the level of loops. Okay. Um, and you could do that using a transition relation with PC, but that is not the most efficient way to do. And therefore, here, the technique that CBMC uses, which is, doesn't construct the transition system with including PC, the program counter, but rather it enumerates all symbolic parts from entry to exit points, okay, by unwinding the loops. So in that sense, it gives, the measure there is not the unrolling of the transition system, but it's kind of directly related to some aspect of your program. So it kind of bounds the error that it proves to be the absence of error. The bound of that is somehow related directly to the number of unwindings of the various loops in the program, which makes more sense. We saw that when you did that, the number of paths, because there are branching conditions, the branching conditions in the if then else can, when combined with loops, can have a combinatorial explosion in the number of symbolic paths. We're not even, I mean, even the number of symbolic parts, for you to enumerate, and therefore we introduce the single static assignment encoding for straight line programs. And what CBMC does is the body of each loop is represented as an SSA, and this it it introduces merge points so that the body of the loop is a body of a loop free, the body which is loop free, but possibly has nested if then else, can be represented as a single symbolic path. That's what the SSA encoding does. Okay. And it also obviates the need for requiring PC to be part of the state encoding. And it prevents, to some extent, the path explosion that you get, the combinatorial explosion that you get as a result of the if then else conditions interacting with loop unwinding. Okay. Um, an important aspect is how do you specify the property? I mean, what kind of support does CBMC give for property specification? As I noted, um, Euclid, when I introduce you to that, you will know the details. Euclid supports not only a means of specifying transition system directly, but it supports temporal logic specification, and it supports full first order with the quantifiers and so on to specify your property. Okay, whereas CBMC is it makes a different trade-off. So here, it gives support for specifying only invariant properties, and these are done by annotating your program with assume and asserts. Okay, where both assumes and asserts have a Boolean expression that is expected to hold at those points, okay, at the points where they're intersected. And those things are meant to, they are first order conditions, but it requires them to be quantifier free, okay? So in that sense, it is somewhat limited. That puts a limit on the kind of specification that you can express in CBSC and verify. But where what I wanted what I was trying to emphasize through the example, and I will get to example very soon once I'm done giving you an overview, that it allows what I illustrated, what I called as non-deterministic assignment, okay? Which is a very powerful tool. I keep repeating in this, I mean, I've been repeating, okay, non-determinism is a very powerful tool for not only abstracting, introducing abstractions in your model or abstracting fragments of code, but in combination with the semantics of SSA notation, it can also get you the power of limited effective quantifiers, okay? In assumes and asserts. And that is the one that I want you to pay full attention to when I when we when I illustrate these examples. Okay. Because that's what gives CBMC the power of the specification, and you'll have to not only leverage that and understand it, leverage it in your verification exercises. Finally, I introduced last time the notion, I mean, a feature of CBMC. It's called unwinding assertions. This is used as a means of checking if my current unwinding level, the unwinding number, is uh, is incomplete. This is a check to see if it is incomplete. Okay. Look, of course you can, yeah. So the only way to ensure the completeness of bounded model checking verification technique is to compute the completeness threshold. That is, somewhat easy to, it is expressible when you do it as a transition system. But when you're unwinding loops like that, like here, then it becomes quite complicated to even define those completeness threshold. And that's why this unwinding assertions is a uh, cheap inexpensive way of at least checking if it is still incomplete. It doesn't the feature doesn't allow you to compute the completeness threshold. That's not what it is intended for, but it has an implicit check to see if you need to do more unwinding. Okay, and that is another key aspect that you will have to understand and leverage to see how far you have gone. The bounded model checking has taken you, how far you are from getting full guarantee of a proof of that a completely verified code. Okay, so yeah, this is kind of an overview. I know it's a very high level overview. Any questions here? Before I switch to uh, illustrating examples. Yeah, your next assignment will test you on all these aspects. Okay, and be aware of that. Okay, there will be examples, so it's CBMC, and some pencil and paper exercises where I will have you test your understanding of completeness thresholds and so on. Okay, okay. Um, yeah, I think we had gone through up to this point. Yeah. Okay. So what I wanted to do is so there are two ways that when you leave, when you define, when you make declarations here and without any assignment, as soon as you're declared, as you can see here, this assertion, we said that, yeah, at this point, this assertion is false, okay, because I has not been initialized at all. And I is left completely non-deterministic, and that's why this thing is not true. And similarly, this assertion also is expected to fail at this point because although both I and J are uninitialized, which means it can, when it's uninitialized, what CBMC assumes is that it can be any, it can have any value consistent with its type. And since I and j are two different non-deterministic variables, they can, although they're each of them can be non-deterministic, there's no guarantee that they'll have to be taking the same value, and that's why this assertion fails as well. Okay. And yeah, so CBMC is consistent, it's completely precisely consistent with standard ANSI semantics, okay? And therefore, if you declare a global variable, since ANSI initializes all global variables, therefore, there it'll automatically constrain them to be as per what ANSI initializes them to, the global variables. There's another way, you could explicitly, at any point in your program, force a variable to be non-deterministic. Okay, now for example, here, I mean, although I and J were already non-deterministic, even if you had an assignment, something like this, yeah, you see, equals 0. Suppose I had something like that, which means, and after that, you could, uh, you know, force it to be non-deterministic at that point. So in this assignment, see, it is assigning, it's like a trick. It is using, non-dit and non-dit bool and non-dit uint are just functions without bodies. Okay, they're never defined, and therefore they effectively return some non-deterministic Boolean, non-det bool, and non-deterministic unsigned integer in here. So when you do this, then after this point, I and j will take two distinct, not necessarily the same non-deterministic values. Okay. As you can see, at this point, as per SSA notation, I mean, what internally I would have a value 0, and this makes it expands its thing. Okay, so because this includes I is equal to 0 as well, there's no inconsistency being done here. So whenever sorry, okay, yeah. So anyway, it is then changed, and even if you had something like this here, okay. You see, at this point, they are two different ones. And now, okay, let me go one step at a time. So once again, I is equal to j. This won't be true, correct? Yeah. Here, why? Any of you? I'm claiming that,
Excuse me, sir.
yeah.
Sir, I have a question. Why are there two asserts there? One is assert and another is C prover assert.
Yeah. I think that's the same. See, prover assert takes two arguments. Okay. Where do I have assert here? Here,
Um,
on
uh,
this line. Yeah.
because I think C has a function assert as well, which does this only.
It could be that maybe you might be right. But I think CBMC, this works as they assert as well, I think. Okay. And I need to check that. Okay. Certainly C prover assert is the is that I believe assert also works, but that needs to be double checked. Another difference here is when you use C prover assert, it takes two arguments. The second argument is some tag, that a label that you can give that particular assertion. Okay. Yeah.
Okay, sir.
Yeah. So now here, see what I'm doing here. So this is something that last time I insisted that you need to watch out for. Okay. I is equal to, I'm assigning length plus 1 to I. Length itself is 4, defined as a constant 4. So it's 5. Now, if I do this, okay, what will happen? See, this kind of thing, when you when you introduce assumes, you always need to make sure that your assumptions are what you want, but certainly your assumptions have to be consistent. Okay. You cannot introduce inconsistency. See, you can always start with, okay, in this case, eyes length plus 1, but here you're making, when you do an assume immediately after this assumption will be made on the timestamped variable that is resulting immediately after this assignment I. And therefore, here you see your I is being, the value, the latest value of I is like plus 1, which is fine. But here it is insisting that it has to be between 0 and length. So effectively, internally, what it does is it just, uh, the formula representing the behavior of this program is a conjunction of all the individual piecewise SSA generated for each assignment statement. And then these assumptions are just the constraints that are added as one of the conjunct on the latest value of this variable. Okay. So that is inconsistent. Okay.
Excuse me,
So
sir.
that's why after this point, what will happen is pretty much what you have is now false. Okay. So false can be used to prove anything. And therefore, if I did something like this here, okay, firstly, do you see why this is inconsistent? Anybody has any doubt about why?
Excuse me, sir.
Yeah.
Yeah. Uh, like if we assume that I and len both are unsigned integers, and then if we take length to be the maximum possible
No.
value in
Yeah,
C,
yeah, but that
then
is true. But I
shouldn't
have
it
defined
roll
length.
back to so, oh, sorry, sorry. Okay.
Yeah,
It's
because
like
length is a
yeah.
constant, no? Yeah, you're right. If
Okay.
length were a variable and which is unassigned, then what you said would be true. Okay. Um,
Yes,
but
sir.
even then, that would be a specific value, even on that thing. So, but then there isn't. But yeah, but the bottom line is, even if length were non-deterministic, yes, then I would be completely non-deterministic. Then this is okay. You're right, Lucky. That's a very good observation. Okay,
No,
if
sir,
length,
Somil said.
huh?
Sir,
Yeah.
it was Somil.
Oh, sawmill,
Was
is it? Okay,
said
good.
this.
Um, yes, if length were left non-deterministic, then I would be completely, could be any unsigned integer, and constraining this way is okay. Very good observation. Okay. So, but since length is defined to be a constant, this would give rise to an error. Okay. This would give rise to an inconsistency. See, this introduction of inconsistency is a bane of any verification tool. Okay. Verification in a formal verification is a great thing when used like any technology. It has to be used carefully by understanding its uh, pitfalls, limitations, strengths, and weaknesses. Okay. So, I mean, assumes are a great thing because they can constrain your inputs. And as you can see, it can also now be, I mean, used to abstract fragments of code, but you have to use it carefully, to ensure that inconsistencies are not introduced. Okay. So, and the common trick that I use in any verification tool for that matter is, if you're using, think through, okay, whenever you do assumes, and here the assumes, by the way, when you introduce an assume, that assumption takes effect from this point onwards. Okay. So so all assumes have to be mutually consistent with each other, number one. Number two, that they'll have to be consistent with the latest value, that latest values, that all the variables that are used in the expression, in the propositional expression that is being assumed. Okay. So both. Anyway, getting back to this thing, when I'm not sure, I mean, one way of double checking that my assumptions are not inconsistent is to introduce try to verify something like this. This assertion is trying to verify false. If if CBMC says, oh, false is verified, aha, then you know that there is some inconsistency that you have introduced at that point. So if your number of assumptions, etc., are getting too complicated or you're not sure, you can always do this. and then double check. Okay. Um, yeah, I mean, yes, that is one. Let's see. What am I doing here? So here I'm assigning a non-deterministic value to L. Then I'm constraining it here on line 51 to be between 0 and length minus 1. Yeah, so this one will not be true because why? Because I'm assuming that I have eliminated this, say, where am I? Yeah, even with or without this, L will not be equal to I, right? Even assuming I is Yeah, even assuming I is constrained to be, if I is length plus one without this assumption, even then it'll definitely not be true. Even if I is constrained to be between 0 and length minus 1, this is not true. Okay. So, yeah. So that's what is being said there. This, I think I'm illustrating the same thing. So I'll move to arrays here. The the need for quantifiers, etc., will be more pronounced when you're uh, trying to specify properties that you want to check over array manipulating programs. Okay, arrays by nature are containers of elements, and therefore you need to be able to say things about specific elements inside the array. So here, for example, I'm initializing an array to 0. Okay, and suppose at this point I have defined I to be, suppose I have something like this. Okay, so I is between 0 and len minus 1. So now what am I doing here? I want to assert that every element of the array, my array, is 0. Okay. And by using non-determinism, let me move this thing here so that you will see. Okay. So I is non-deterministic. It can be any element between 0 and length. Okay. So what I'm asserting here is that my array I, where I is anything between 0 and length minus 1, has to be 0. Okay. This effectively gives you the semantics of saying for every I between 0 and length minus 1, my array is equal to 0. And the reason that you get that is because it always checks what CBMC does internally, what ships it off to SAT solver is the SSA notation of everything that you have encoded up to this point. And this assertion, the negation of this assertion is shipped, is added to it. I mean, it checks if this implies the negation of this assertion. Okay, that is, it is checking the validity of that. If this is unsat, okay, then it checks if it is unsat, then it means it is valid. So if it is valid, then it means that it is true for every every instance of I that is permissible. Therefore, you get the effect of having universal quantification because it is checking if it is unsat, then it is, if it is sat, of course, it means that it is not true for some element of I. But if it returns successful, that means the negation of it is unsat, and therefore this thing is valid. Okay. And that's why you get the effect of universal quantification. Every time that you can use this trick in order to get the effect of universal quantification in your assertions. Is this clear? Any doubt?
Sir, I have a doubt.
Yeah.
Sir, when you're doing this C prover, assume I is less than L and L less than length and greater than equals to 0. Doesn't it, for example, if I have just one entry in my array that is 0, then also it will satisfy. Uh, that's what I wanted to ask.
No, but this has to be, if
I
it
mean, my
is,
point is that not all entries in the array should be 0. That's since if I mean I can always, if there exists at least one entry in my array that is 0, then won't this satisfy?
yeah,
Probably, I'm
see,
not
this
sure.
is exactly what it is trying to check. Okay.
Okay, okay, okay. So
Yeah. This is what it means. So this is part of the assumption that has been made, and I'm assuming that this is consistent. Okay. So zero is, this is exactly what it does. The assumption exactly introduces that I is between 0 and length minus 1. Okay. So when you do an assume, what it does is all the assignments are encoded as SSA, and this one will say that the latest time-stamped variable of I will satisfy this assumption. Okay. So the timestamp I'm using implicitly, so that is the latest value. So, and this is exactly what it does. The SSA, which includes this assumption, implies that
yes,
this condition is valid. Okay. So you see, so if it's the validity that is checked, so if indeed it verifies this successfully, that means that there cannot be any I, okay, for none of the i's between 0 and length minus 1, that this condition is going to be violated.
yes, sir.
Because this assumption is passed as a precondition. And since this is permissive, it's permissive. So I is, can be anything between 0 and 1. So this one is, uh, yeah, it'll actually check for every I. It has the effect of checking that for every possible I, okay, that that my array of I has, the latest value of my array of I has to be 0. That's what it is checking, no? Because imagine my array of I is like a bunch of variables. Yeah. An array is like a bunch of variables. Yeah. So for every value of I, it is saying I mean, this is valid only if it is true for every possible value of I that is permissible at this point, which is anything between 0 and length minus 1. Okay. And for each of them, it is checking, I mean, this is valid only if this consequent holds good for every I. Okay. This is exactly what it's checking. And therefore, that unsat will, I mean, if that is true, or there's no, the negation of that is unsat, okay, which is what I'm being checked here, Okay, it's just checking if it is possible to assign, to find, if this is checking if there is a value for I between 0 and length minus 1 such that my array of I is not equal to 0. Okay, if there is unset, then it has to be, all of them have to be 0. Yeah. 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 Is that clear now? Yeah. Okay.
Yes, sir.
Similarly here, yeah, you see, you get the power of existential quantification if you used this non-deterministic assignment. This is what I call as non-deterministic assignment. Here, I'm assigning a value of k, but not a specific value to k, but rather I'm constraining the permissible value of k to be between 0 and length minus 1. Okay. This is what I call as non-deterministic assignment. So it allows K to be anything between these two. Okay. For any particular run, it may be, so anything that you check as a result of it has to be either sat or unsat for every possible value of this thing. So, no, this is the same thing. Okay, no. Okay, no, I want to concentrate on this. This gives the same thing. So here, see, prove or assert my array k of x is true. It's the same thing as this. No? I'm assigning, what am I saying here? Yeah, here I'm assigning my array of I to be equal to x. It assigns an element at some arbitrary element to be s. Okay, and you could check this, okay, to be true or not. So here, so after this point, okay, I'm saying if this is valid, okay. So at that point, because you're assigning x, that is true. What I really want to draw your attention to is this one. Okay, you will get the assumption, you will get the effect of existential quantification in assumptions when you use non-deterministic I. Okay, if I is between 0, any value between 0 and length minus 1, then if you make an assumption like this here, what you get is this assumption will be added as a precondition to any property that you wish to prove. Okay, because this assume itself, whatever you have in the assume, will appear in the precondition of your validity checking for any assertion. Therefore, that gets negated, not A of R. Okay, so when you have this, what it means is that there exists some I between 0 and length for which my array of I is equal to x. Okay, but that I could be anything. Okay, so there is at least one element. You don't know which one it is. Okay, yeah, it's as though saying either my array of 0 is equal to x or 1 is equal to x and all the way up to length minus 1. Okay, and that's what you get. Okay, so if it is in assert, because it appears in the validity checking, in the consequent, you get the effect of universally quantification over I. Okay, and if it is in the assumption, you get the indirectly with the effect of existential quantification. Okay, so these two things can be used to yeah, and that's what I illustrated here in the um, last time, and I will end with that. Yeah, and I guess yeah, you already, generally the people who showed up, they didn't have any objection. So here you see, I'm leaving, I mean, I'm constraining Z to be between 0 and 4. And after that, I have left I to be completely non-deterministic. So when I make an assumption like this, which I'm further constraining Z to be something equal to the effect of shifting one I positions to the left. And if you put these things together, and that I being non-deterministic, what it means is there exists an I such that when one is shifted as many times as I, whatever the value in Z must be equal to it. And therefore, as we saw, that this has the effect of constraining Z to be not only between 0 and 4, but to be a power of a power of 2. Yeah. Yeah. So, yeah, so that's the idea. So, was there a question? Okay.
That's all.
Okay. And you can see here, you can do this. Here is a binary search program, okay, which searches if an X, if a given element X is present in an array, assuming that the array is ordered, okay, in increasing order, I guess. Yeah, I mean, yes, in increasing order, strictly increasing order. So that's what I'm doing here. See, you can't get and here it illustrates the thing. So this is doing a simple binary search. Of course, it will work only if your array is ordered. And that is the assumption that is being made here. And since you can only get, so as I illustrated, you can get the effect of you universal quantification only in asserts using the non-deterministic assignments for some I that you're quantifying over. Okay, but but if you want to make assumption, there's no other way other than actually making the assertions one proposition at a time, okay, over each propositional variables. So and that's why I'm using a for loop here to make that assumption. Okay, so here I'm literally assuming, I mean, enumerating all elements of the array and constraining every consecutive pair to be ordered as per this less than. Okay. So, whereas if you were, yeah, because in assumptions you can leverage the SAT unsat assignment semantics to get the power of existential quantification. That is not possible when you are doing when you want to have to make a universal assumption, okay, a universally quantified assumption, and therefore then you're forced to use a for loop. Okay. Similarly, if you want to do some checking. So here I'm assuming the thing, and then let's see. So then I'm invoking the binary search thing, checking if X is inside the array. And this, the way it is implemented is it returns -1 if it does not, or it returns the index at which it finds X to be stored in the array. Therefore, I is here either -1, or if X is absent, or if it is present, it'll be the index at which it is present. So then you can prove things like this. Okay, all these things are yeah, here I'm saying, oh, I has to be between -1 and length -1. Yeah, here what I'm saying is if I is non-negative, then it has to be present in the array. And here I'm using, yeah, I'm proving something which is universally quantified by saying if I is less than 0, yeah, here I'm saying if I is less than 0, I'm explicitly saying if I is less than 0, then it X can never be in any one of those thing. Okay, it's the converse of this. So if I is negative, then every element of the array has to be something distinct from X, and that's what I'm proving. This is a universally quantified thing, and I'm getting that by using this non-deterministic assignment. There, I don't need to use a for loop. If you want to do there exists, then sometimes you will have to then you'll have to use a for loop. If you want to prove an existential quantified assertion, then you will have to use um, might have to use a for loop in your to get that power of expressing that assertion. Okay. Yeah, so this is where I want to end today. I mean, if you have any questions. So I have uploaded all these files into a folder to the Google Sheet. So I encourage you to install CBMC and start running and checking these, running these files. And your next assignment will be on merge sort. Okay, to prove some properties about merge sort. Okay, which I will upload and I'll discuss next time. Okay, yeah. Okay, I'm going to stop here unless you have questions. Okay, thank you.